Suppose I have a block in a 2D space here. This is the X maybe, and this is the Y. And I were to apply a shear force to the upper surface of this block, like so. Then the block would distort in this fashion. This angle here is gamma, and we call gamma the shear strain. So if that's gamma, this is pi over 2 minus gamma. And this angle is pi over 2 plus gamma. So the sign convention we want to use is shear strain is positive when the shear load or shear force is positive. And if you recall, shear force is positive when it acts on a positive surface. So this is the positive surface, this is the negative surface. So if the force is acting on this surface in a positive direction, which it does to cause this, it's heading towards the positive direction of X. So that's positive shear strain also. And the opposite is true, negative. So it's negative when the shear load is negative on the positive face. Now we can plot stress strain curves for shear just like we did stress strain curves for our normal stress and strain, so tau and gamma. And initially the curve is going to follow linear elastic for, say, a ductile steel material, where this slope is something we call G. So G is the shear modulus, just like E was the elastic modulus. And so therefore tau equals this constant G gamma. Sometimes we call the shear modulus the modulus of rigidity. Rigid material is one that doesn't shear much. Let's look at an example. Now say we were given this bearing pad over here on the left, and we apply a shear force to this surface. So given this bearing pad under horizontal shear, we want to find the average shear stress and strain. So what's going to happen here? We're going to apply this shear stress. So if I'm looking at the side view of it, we're going to apply this shear stress, and our bearing plate is going to deform. So our bearing plate has a dimension of A here. So it's going to deform like this, and we're going to have a shear strain associated with this angle, and it's going to be positive because this is the positive side versus the negative side down below, and it's in the positive direction. I suppose we're going to define it as positive because we'll make this X and this Y. And I just realized I drew B incorrectly, so B is actually the width over here, H is the height of the pad, and A is the length. So if I'm going to plot or calculate my average shear on this, we're going to have V V over the cross-sectional area A that V applies to, which it means that we're going to have V divided by the dimensions A times B. And that's our average shear stress. Now, to take it a step further and look at our average shear strain, or our shear strain, then we could go with gamma equals, and as we mentioned before, gamma is a function of shear stress. So our shear stress divided by G equals gamma. And we can write that in terms of shear force as V over A times B times G. So if we need the values, any of these values, we could actually calculate that. Recall that G here is our shear modulus for our material. Now we can relate G, the shear modulus, to our modulus of elasticity E with this equation. G equals E over 2 plus 1 plus nu. So that's how those two relate. Let's go ahead and box that.